The James Webb Space Telescope is identifying objects in the dark ages that, by best measurements we have, are large, fully developed galaxies. So who ordered that?
We are losing contact with the cosmos, and things are only going to get worse. The unexpected information gathered by the James Webb Space Telescope provides compelling evidence for this theory. The James Webb Space Telescope, which was launched on December 25, 2021, has given astronomers a whole new perspective on aspects of the solar system and cosmos that they had never before understood. NASA's $10 billion time machine takes us beyond what has been seen, more than predicted, from planets in our solar system to merging galaxies and deep space nebulas situated millions of light years away. James Webb's Deep Space Telescope discovered something astounding. 900 trillion stars have inexplicably disappeared into space, and the situation is growing more terrifying by the second. What took place? The stars vanished, but where? How could they have vanished completely without a trace? Join us as we explore this startling finding made by James Webb in further depth, learning about features we've never seen before and the potential implications of the departure of so many stars for our planet and future. First, just to let you know, the process by which we locate and verify the existence of distant galaxies is actually rather simple, at least in terms of astronomy. All you have to do is take these actions. 1. Initially, you collect as much light as you can from a designated area of space and hold onto it for as long as you can. 2. Subsequently, you photometrically collect that light over a large field of view in many filters, first to find ultradistant galaxy candidates based on the locations of the light's appearance and absence. 3. Next, using spectroscopy, you study the most promising ultradistant possibilities. Here, you can exactly identify how redshifted the light from each object is by dissecting its light into its component wavelengths at a high precision. 4. Eventually, you ascertain the characteristics of this galaxy, including its age, brightness, distance, and size, using the gathered data, an inferred gravitational lensing map, and the known characteristics of our universe. While this may seem straightforward, the truth is that your telescope or observatory specifications will essentially determine how much and what kind of light you are able to collect. 3 key distinctions between Hubble and James Webb are instantly apparent when we compare them side by side. These variations include those in size, such as the primary mirror's size, color, such as the color coding used on the mirrors and optical components that comprise the observatory, and temperature, which is difficult to perceive but is a crucial component of the telescope's construction and design. Hubble is equipped with a 2.4-meter primary mirror, a silvery clear reflective coating optimized for reflecting optical light, and a highly reflective coating covering the entire observatory to reflect UV, visible, and infrared light away from it. This light originates from the sun, which shines on it for approximately half of the day, and the Earth, which radiates heat from a mere 500 to 600 km distance. But for James Webb, we have a primary mirror with a diameter of 6.5 meters, a gold-colored reflective coating that is ideal for reflecting both near and mid-infrared light, and the observatory itself is situated 1.5 million kilometers from Earth, where it is constantly protected from the sun by a unique passive cooling system called a sunshade. Moreover, James Webb's mid-infrared instrument is equipped with a second, specially designed cryocooler that actively cools it down to a mere 6 to 7 Kelvin, making it the telescope's coldest section. These variations result in radically distinct characteristics about sensitivity for these two observatories. With its infrared lens, James Webb can see far farther into the deep cosmos and the distant past than Hubble, and estimates place its power at a factor of 100. In a breathtaking discovery, the telescope saw billions of stars vanishing into thin air as James Webb concentrated on vast swaths of space that looked empty to Hubble's sight. However, how far did they go? The two main theories about what happened are that either they just end their existence with a whimper, not a bang, and sink into a black hole of their own making without the light and fury, or they're still out there, still erupting their way through their death throes with less luminosity and possibly obscured by dust. We must first give you a crash course in stellar evolution in order to help you grasp this concept. Nuclear fusion reactions in a star's core convert hydrogen into helium and provide energy. When stars 8 times as massive as our Sun run out of hydrogen, they begin fusing other elements, such as helium, carbon, oxygen, and so forth, until they have an inert iron core that needs more energy to initiate the fusion reaction than it can generate. At this point, the fusion processes stop and the star's ability to produce energy vanishes. When gravity suddenly takes over, the star's core collapses and the outer layers bounce off the shrinking core, exploding outward and igniting a supernova that, for a few weeks at most, can shine brighter than a whole galaxy. In the meanwhile, a compact object is formed by the collapsing core. This object is often known as a pulsar, which is a spinning neutron star, but, in some circumstances, it may also be a stellar mass black hole. This is how outstanding timelines often work. Astronomers are starting to accept, nevertheless, that some stars may be able to form black holes without exploding like a supernova. Failure supernovas, or stars that brighten as if they are ready to explode but then falter and fade away, have sometimes been observed by researchers. Numerous stars that are no longer visible have been discovered on ancient photographic plates that have been analyzed as part of the vanishing and appearing objects during a century of observations. VASCO project, which is headed by Beatrice Viller. It appears as though they had disappeared completely. Are these failed supernovas and disappearing stars proof that stars are nearly completely drawn into the black holes they produce before they get an opportunity to explode? Okay, perhaps. According to some scientists, yes. It's interesting to note that, although being only a hypothesis, the notion now has solid backing in the shape of a peculiar binary system called VFTS-243 that Vigna Gomez and colleagues have researched. The system is housed in the Large Magellanic Cloud's Tarantula Nebula and was found there in 2022. It has a 10 solar mass black hole and a 25 solar mass star that were both formed by a big star that, in cosmic perspective, must have ended its life quite recently. There are no signs of an explosion in VFTS-243, despite the fact that the star has fallen into a black hole. In VFTS-243, for instance, the black holes and stars' orbits around their shared center of mass are still almost perfectly spherical. Nonetheless, asymmetric supernova explosions emit somewhat more energy in one direction than the other, which ought to provide a natal push to the compact object that develops. A kick like that would speed up the compact object and lengthen and expand its orbit. The black hole in VFTS-243 has only been kicked by a maximum of 4 kilometers per second. Normally, this kick occurs at speeds of between 30 and 100 kilometers per second. The effects of natal kicks have never before been seen in stellar mass black holes, but they have been previously detected in pulsars. VFTS-243 provides the best view of the outcome of this process to far, and it is quite likely that this is providing some insight into the formation process of stellar mass black holes. 3 processes result in natal kicks: gravitational waves, a neutrino burst from the star's collapsing core, and debris ejected from the exploding star. But without the supernova, there would be no debris, so the only things left to give. A far smaller kick would be the neutrinos and the gravitational waves, exactly what we find in VFTS-243. If this is true, it implies that a large number of the universe's most massive stars, which blaze so brightly, die silently as they are drawn into a black hole's abyss. When the surviving star in VFTS-243 reaches the end of its existence, this may also be its final fate. Wider effects are also seen. A supernova explosion's wrath is an element factory. In addition to being launched into space, where elements like oxygen, carbon, and nitrogen found in a dying star's outer layers can be recycled into new stars and planets, supernova debris can also form heavier elements due to the intense heat and energy of the shock wave. For example, cobalt and iron are formed as a result of the radioactive decay of nickel isotopes created during the explosion, which explains why supernovas light for such a long time. Nevertheless, if certain big stars are entirely collapsing into black holes in the absence of supernova explosions, then they are unable to participate in the production and recycling of elements that construct Earth-like planets, maybe even capable of supporting life on their own, from components derived from exploding stars. There is another scenario that we cannot rule out, even if more proof is still needed for the theory that stars disappear into their own black holes. In the worst situation, there is nothing we can do to stop the cosmos from simply vanishing. The idea that the universe is expanding and that galaxies are traveling faster away from us the further they are from us was originally proposed by physicists about a century ago. This is due to the fact that the universe is filled with gravitationally bound objects and that the fabric of space in which they live is expanding, not because galaxies are physically moving away from us. However, this perception, which was prevalent starting in the 1920s, has lately been updated. Only 20 years have passed since. We first saw that this expansion was accelerating and that, over time, galaxies will appear to be moving away from us at an ever-increasing pace. Even traveling at the speed of light won't be able to reach them in the end. Because light travels at a fixed speed, a star that appears to be 100 light-years away from you is actually 100 light-years away when you look out at it. However, you are not gazing at a galaxy that is 100 million light-years away when you gaze at one whose light has arrived after journeying toward you for a total of 100 million years. Instead, the galaxy you're viewing is far further away than that. This is because, at the biggest scales, the cosmos is expanding, including things that are not gravitationally bonded to form galaxies, groupings, or clusters. The cosmos is expanding at a faster rate the longer it takes a photon to travel from a distant galaxy to your sight. This suggests that the farthest galaxies are actually even farther away than the time it has taken for light to journey there. The result manifests as a cosmic redshift. We completely anticipate that light will arrive at its destination with a certain wavelength as it emits light with a specific energy and, consequently, a specific wavelength. That wavelength would be the same if the universe's fabric were constant and neither expanding nor decreasing. However, as the video above illustrates, when the cosmos expands, the fabric of space stretches, lengthening the wavelength of light in the process. This image has been confirmed beyond doubt by the huge redshifts we have measured for the farthest galaxies. However, our abilities extend well beyond simply seeing that the cosmos has grown and will continue to grow. With the use of all the data we have gathered, we can determine how the cosmos has grown throughout time, which helps us determine what makes up the universe. The light's wavelength is stretched by the expanding universe as it departs from a far-off cosmic source. This results in a redshift, whereby the farther-off objects will maintain their light redshift for longer periods of time, depending on which aspects of the cosmos had greater significance. We may recreate the whole expansion history of the universe by observing sources over a wide range of distances, determining their redshift, and then comparing either their intrinsic against apparent size or their intrinsic versus apparent brightness. We can also learn about the composition of our universe, which consists of 68% dark energy equivalent to a cosmological constant, 27% dark matter, 4.9% normal protons, neutrons, and electron matter, 0.1% neutrinos and antineutrinos, roughly 0.8% photons, and nothing else at all, no curvature, no cosmic strings, no domain walls, no cosmic textures, etc. The universe expands because of the different types of matter and energy that are present within it. Once we have this level of precise knowledge about the elements that make up the universe, we can easily apply it to the general relativity principles of gravity to ascertain what will happen to our universe in the future. When we first applied this to the finding of a universe dominated by dark energy, we found something startling. It meant, first of all, that any galaxy that was not gravitationally tied to us would gradually fade from our field of vision. Without any resistance from gravitational pull or any other force, the universe would keep expanding and they would accelerate away from us at an ever-increasing pace. A galaxy would grow farther away with time, indicating that there was more space between it and our own galaxy. The expansion of space gives the impression that the galaxy is moving away at ever-increasing speeds. But this leads to an even more unsettling, unavoidable conclusion. It means that a photon that is traveling from our galaxy to a distant one or that is approaching our galaxy from a distant one will never reach us at a certain critical distance from us, because of the expansion of the fabric of space itself. Even if we traveled at the speed of light, we would not be able to reach distant galaxies due to the universe's rapid expansion. Since the density of matter and radiation is still decreasing and the pace of expansion is slowing down overall, that distance is currently only around 18 billion light-years. Given that the radius of our observable universe is approximately 46 billion light-years and that all regions of space have the same number of galaxies, this means that, even if we left today and traveled at the speed of light, we would only be able to reach about 6% of the total number of galaxies in our universe. This implies that between 20,000 to 60,000 stars, on average, change from being accessible to unreachable every second. The light that they release this very second will never reach us, but the light that they emitted a second ago will. Though that's a depressing and unsettling idea, there is a more positive way to look at it. The cosmos is trying to tell us how valuable each and every second is. The cosmos is reminding us that every second we waste is another chance lost if we ever wish to venture beyond of our own local group, beyond the gravitationally confined collection of objects that includes Andromeda, the Milky Way, and around 60 minor satellite galaxies. Just 6% of the estimated 2 trillion galaxies in our universe are still visible from Earth through the Milky Way, and that percentage is steadily declining. Because of dark energy's acceleration of the universe's expansion, 94% of the galaxies in the visible universe are already beyond the grasp of humans. As time passes, every galaxy outside of our small group will ultimately suffer from the same destiny. Humanity will be trapped in our local group for eternity until we discover a way to go across galactic boundaries and explore other galaxy groups and clusters. Our capacity to transmit and receive messages to the vast cosmic ocean will eventually disappear from view. The cosmos is expanding at an accelerated rate, and our gravity is not powerful enough to stop it. There is nothing that we can do to stop the cosmos from fading. How it will all end is one of the most profound existential questions we can ask ourselves at that point. We have discovered that not only is the universe expanding, but that the expansion is speeding thanks to our current observations of it, our understanding of the rules that govern it, and the way that the things inside it all seem to be moving away from us. With the passage of time, far-off things outside of our small group continue to accelerate away from us, until finally the universe is driven by dark energy and is empty, cold, and lifeless. In accordance with the data, the majority of us believe that dark energy is a constant in space and that its energy density doesn't change anywhere. However, if dark energy becomes stronger over time, that would drastically alter our destiny and result in what is known as the Big Rip. In order to comprehend the Big Rip, we must first comprehend the rationale behind its consideration, the evidence supporting the existence of dark energy. There were two distinct effects competing for dominance if you were to picture the cosmos in its early phases, right after the intense Big Bang. The initial expansion rate is the first and aims to break everything down as fast as possible. The gravitational pull of all the matter and energy in the cosmos, which aims to bring everything back together and collapse the universe, acts as an opposing force. Most of us would conjure up three distinct outcomes, something like the story of Goldilocks and the Three Bears. Since distant objects continue to recede indefinitely, it is possible that the universe's matter and energy are unable to keep up with the expansion rate, which decreases but never approaches zero. Maybe the universe is growing too slowly, reaching its maximum size before compressing, imploding, and ultimately terminating in a big crunch. Maybe everything in the world is exactly balanced in terms of both its gravitational pull and its rate of expansion. If there had been one more atom, the cosmos would have imploded, but as it is, we are only one atom away from that doom. However, none of these ideas fit with what we see the universe doing. That perfectly balanced model seems to fit the data for the first few billion years. But then an odd thing happened. Had you been seeing any specific galaxy, the influence of the expanding universe would have been visible in the light emanating from that galaxy. The expanding cosmos expands the light's wavelength from the moment of emission to the moment of reception, causing the light to be progressively moved towards the red. The redshift is proportional to the total amount of expansion that has taken place and is comparable to the apparent recession velocity over time. If you could have measured that redshift for any object at all, you would have seen that it began very large, gradually decreased over time, looking as though it would asymptote to 0, and then, after reaching a minimum value, abruptly stopped decreasing and started to slowly but steadily increase once more, continuing to do so until the present day. What is amazing is that if a world with only radiation and matter, both dark and normal, exists, then general relativity cannot explain this result. It cannot be explained by spatial curvature either. We need a whole new kind of energy, which we now refer to as dark energy, to explain this observed phenomena. Possibly the most widely accepted, and by many measures the most convincing, possible explanation for dark energy is that it is just a type of energy known as a cosmological constant, which is present uniformly across space and has a constant energy density. Dark energy would simply maintain a constant energy density and cause all gravitationally unbound objects to accelerate away from one another at a constant rate, with their recession velocity increasing linearly with time. If it is the cosmological constant from general relativity, the zero-point energy inherent to space from quantum field theory, or some other kind of field akin to a scalar or pseudoscalar field that coupled equally to the universe at all locations and at all times. If this is a correct description of dark energy, then we have a fairly accurate idea of what will happen to our universe. The greatest bound structures will never become unbound from one another, and all existing gravitationally bound structures, including as solar systems, galaxies, and groups and clusters of galaxies, will stay gravitationally bound. Everything will keep expanding and getting faster until all possible transitions have occurred and there is no more energy left to be drawn from any physical process in the cosmos. However, this need not be the case. When we combine the best observations we have, which come from distant individual objects, the large-scale structure of the universe, and the temperature and polarization data from the cosmic microwave background, we find that dark energy is consistent, within an approximate 8% error, with a cosmological constant. It is still plausible, though, that dark energy is a dynamically growing quantity that just evolves in a way that isn't detectable given the limitations of present observation. It's possible that dark energy may completely vanish if it does develop, bringing us back to the just right Goldilocks scenario. It will eventually weaken and change sign, which means that our universe will really compress during the Big Crunch. Alternatively, and this is certainly the most intriguing possibility, it may get stronger over time as the cosmos gets older and its energy density rises. The last scenario, where dark energy gradually becomes stronger, leads to a big rip, in which structures that would ordinarily be stable in the universe finally get to a point where the universe's expansion has the capacity to destroy every single one of them. The only thing that will distinguish a universe with constant dark energy from one with rising dark energy over many, many billions of years will be the degree to which the expansion rate varies, or how much the light from far-off objects is redshifted. The redshift grows at a greater than linear pace with time as dark energy increases, as opposed to growing dark energy, which causes the redshift to increase linearly with time. If there is no restriction or limit on this rise, it will ultimately start to negatively impact these massive bound structures. As the outlying galaxies break free from the cluster and are sent into intergalactic space, the largest and most extensive galaxy clusters will first begin to separate. The tighter, denser parts of clusters and finally galaxy groups are also torn away until we are left with nothing but individual galaxies. Then, from the outside in, the individual galaxies will have their stars, gas, and dark matter plucked out of them. Eventually, even the galaxy's cores are reduced to their individual star systems, starting with the outermost regions of the galaxies. Then, near the end, separate solar systems are destroyed. The Kuiper Belt objects, the outer planets, the asteroid belts, and even the inner planets are stripped away, starting with the frozen worlds of the Oort cloud. Ultimately, the separate structures, like planets and moons, are disassembled into their component parts. Just moments before the very fabric of space and time is destroyed by dark energy, molecules are split apart into their constituent atoms, electrons are stripped of their nuclei, and atomic nuclei are ripped apart into protons and neutrons, which are further divided into quarks and gluons in the penultimate instance of the universe. This may sound like a far-fetched scenario, but keep in mind that all of these events are simply unavoidable if dark energy intensifies with time, and there is no limit to the length of time that may pass. When is the only question left? Fortunately, we can determine how long it will take until each phase takes place based on the characteristics of dark energy and how its strength varies over time. The initial stage was originally estimated to happen in as little as 22 billion years, but it will now likely take place at least 60 to 80 billion years from now. But after that initial phase, destroying buildings on a size of around 20 million light years, everything else moves along rather swiftly. It will take just hundreds of millions of years for dark energy to become strong enough to begin overcoming the enormous force of gravity for the most weakly attached objects. Until then, all galaxies will be pulled from their home groups and clusters. After then, stars will be torn from their respective galaxies in a matter of tens of millions of years. Subsequently, the outer planets will be torn from their parent stars in a matter of months, and the inner planets will follow suit in a matter of weeks. Our world will only be completely destroyed in the last few minutes, and it will only take a few nanoseconds for molecules, atoms, and other elements to be destroyed. There is a relationship between the force and energy needed to break anything and the length of time left till the universe ends. The most terrifying aspect is that, despite how unsettling that seems, there appears to be solid evidence pointing in the direction of that outcome. Luckily, the cosmos isn't going to blow itself up very soon, even if we do have a phantom energy situation. It would take hundreds of billions of years for the Big Rip to occur given the existing measurement restrictions. Otherwise, we must accept the reality that at some point we will have to deal with energies and temperatures so high that we have never explored them, even if the Big Rip is only one scenario for how the universe may end if dark energy rises with time. Everything that isn't ruled out is still feasible under those regimes. The fact is that our understanding of dark energy is so limited that all we have to rely on is what observations require of it and, consequently, what is not possible. The cosmos must include a novel type of energy that cannot be explained by matter, radiation, or spatial curvature. It cannot be bound by substance and has to be dispersed uniformly over space. Furthermore, it has to align with a cosmological constant or an energy type that is part of space itself, as far as current measurements allow. We don't really have any solid limits beyond that, though. Dark energy may or may not have existed in the first 10 to 15% of the universe's existence following the Big Bang. It's possible that dark energy is a holdover from the early stages of inflation. It is possible that dark energy is a very new and emerging phenomena. Furthermore, dark energy may be steady and unchanging, or it may be gradually growing stronger or weaker, or it may be preparing for a shift that will occur in the long future. Scientifically speaking, the only reasonable course of action in situations such as these is to go out and collect additional superior data to aid in our search for understanding. Measurements, not theoretical acrobatics, will lead the way if dark energy is known to vary over time. All we can do is keep an open mind and accept the most straightforward explanation as the most plausible until we learn more than we do now. That all might, however, alter very quickly. We should always be cautious when making assumptions that aren't supported by evidence, since the universe has shocked us in the past and most likely will do so again. That's all the information we have for you today. Share your opinions in the comments below. Thanks for watching another episode. While you're here, you can watch more space-related video.